All right, let's get right into it. We all use our computers and phones every single day, and they pull off this incredible magic trick, right? They seem to be doing a dozen things at once, and they don't even break a sweat. But how? How do they actually do that without just grinding to a complete halt? Well, today, we're going to pull back the curtain on the unseen engine that makes it all possible.
I mean, seriously, think about it for a second. You're on a web page, a video's playing, some big, complicated image is loading further down, but you can still scroll around totally smoothly. The whole thing doesn't just freeze up and die. See, that's not one single task chugging along. It's actually this beautifully coordinated dance of many, many smaller tasks. And the secret to that responsiveness? Well, that's what we're here to talk about.
In this idea, it's absolutely everywhere. It's not just in your browser. Take a web server, for instance. It's getting hammered with requests from thousands, maybe millions of users all the time. Now, instead of making everybody get in line and wait, it just spawns a new, tiny little worker to handle each person's request. That's how it can serve everyone at once. But to really get how these tiny workers do their job, we've got to go back to the beginning.
So before we had these incredible teams of tiny workers, computers had a much simpler, kind of lonely way of getting things done. Everything was built around this one core idea, the process.
Okay, so what is a process? It's really just a program that's running. Simple as that. You double-click an icon, boom, the operating system creates a process. But here's the crucial part. Every single process gets its own private, completely walled-off section of memory. Your music player can't accidentally mess with your web browser's memory, and your browser can't mess with your word processor. It's fantastic for security and for making sure one crashing app doesn't take down your whole system. But those high walls, they come with a big price tag. Creating a new process is what we call a heavyweight operation. It takes a lot of time and a ton of resources for the operating system. And because they're so isolated, getting two processes to talk to each other is super complicated and really, really slow. For the kind of multitasking we expect today, just using processes is nowhere near efficient enough. In this picture, it shows the problem perfectly. A traditional process is single-threaded. That just means it has one path of execution. Think of it like a single worker who can only do one thing at a time. If that one task is, say, downloading a huge file, everything else in that app just has to sit there and wait. It's a massive bottleneck, and it's exactly what led to a much, much better way of doing things. And that better way? It came in the form of threads. You know, if a process is the entire factory, then threads are the individual workers on the assembly line, all working together inside that very same factory. So a thread is often called a lightweight process. It's basically the smallest possible chunk of instructions that an operating system can manage. And the real magic here is that you can have multiple threads all existing and running inside of a single process, all working together to get the job done. And this visualizes the difference perfectly. On the left, you've got the old way. One process, one thread, doing one thing at a time. But on the right, you see the modern way. One single process, but it's full of multiple threads. Each thread is running its own set of instructions, but, and this is key, they all share the same resources, like the program's code and data. This team-up literally changed everything. This table just breaks it all down. Processes, they're heavyweight. They're slow to create, slow to switch between. Threads, they're the opposite. They're lightweight, you can create them in a snap, and you can switch between them almost instantly. And because they share the same memory, they can communicate super efficiently. It's like instead of sending a formal, slow letter from one factory to another, the workers can just shout to each other across the factory floor. It's a total game changer. So why should you care about any of this? Well, responsiveness. Remember that browser we talked about? One thread is handling your scrolling, while another one is loading images in the background. That's why the app never feels like it's stuck. They share resources, which is efficient. They're way cheaper for your computer to manage, and maybe most importantly, they let a single program take full advantage of all those fancy processor cores you have in your machine. Now, this ability to run multiple threads at once, it unlocks two really powerful concepts that people get confused all the time: concurrency and parallelism. They sound kind of the same, but trust me, the difference between them is absolutely fundamental. Okay, here is the absolute key difference. Concurrency is like one chef in a kitchen juggling multiple recipes. They chop some veggies, then quickly stir a sauce, then check the oven, then go back to chopping. They're switching between tasks so fast that it looks like everything is happening at once. Parallelism, on the other hand, is like having multiple chefs, each at their own cooking station, actually working on different dishes at the exact same time. One is about smart management, the other is about raw power. This is concurrency in action. Just look at the timeline there. You've got one single CPU core. It works on thread 1 for a tiny fraction of a second, then zap, it switches to thread 2, then 3, then 4, and then right back to 1 again. This is happening millions of times a second, so to us it seems like all 4 are running at once. It's a brilliant illusion, like a master juggler keeping a dozen balls in the air.
And this is true parallelism. Here, we've got 2 cores. And at the exact same moment in time, core 1 is working on thread 1, while core 2 is busy with thread 2. There's no juggling here. There's no illusion. This is genuine, simultaneous work getting done. This is how modern software gets to be so unbelievably fast.
So you might be thinking, great, we'll just keep adding more cores, more threads, and our computers will get infinitely faster, right? Well, not exactly. Multithreading is incredibly powerful, but it is not a magic bullet. There are some very, very real limits.
You know, for software developers, writing code that uses multiple threads is a massive headache. First, you have to figure out how to even break a problem up into smaller pieces that can run at the same time. Then you have to make sure the work is balanced evenly, so one core isn't just sitting around doing nothing. And the hardest part of all is managing how these threads share data without tripping over each other, which leads to some of the most nightmarish, hard-to-find bugs in all of computer science.
In fact, there's a mathematical law that perfectly describes this limitation. It's called Amdahl's law, and it's a really simple but profound idea. No matter how many workers you throw at a project, the total time it takes is always going to be limited by the parts of the job that have to be done in order, one step at a time by just one person.
Now, don't worry about the scary-looking math on this slide. Forget the formula. The only thing you need to look at is that letter S. That stands for the serial part of your program, the piece that absolutely cannot be split up and run in parallel. That one little number acts like a giant anchor, holding back how much faster you can possibly go.
And this graph makes it crystal clear. That red line climbing to the top, that's the dream, perfect speed up. But in reality, look at the other lines. Even if only 5% of your program has to run in serial, that's the green line. Look what happens. By the time you get to about 16 cores, the performance gains just start to flatten out. It's the law of diminishing returns, right there in a picture. You just can't escape that serial bottleneck.
So when you boil it all down, the one thing to take away from all this is simple. Threads, and their incredible ability to give us both concurrency and parallelism, are the fundamental engine that powers every fast, responsive, seamless app that we use every single day. They really are the invisible workers that make modern computing possible.
But that leaves us with one last, really fascinating question to think about. The jump from single-core processes to multi-core threading was a gigantic leap forward. But as our computers keep getting more and more powerful, what's the next paradigm shift? What comes after threads? Now that is something to think about.